So in this example, this is the last example from our packet today. We'll talk about thermal energy, TE, and how to deal with it in problems involving energy. So a couple of statements to make. Number one, thermal energy is not a form of potential energy, and it does not have a formula of its own. Secondly, thermal energy is always dealt with in problems through subtraction, okay, using this relationship. So let's take a look at this. In an energy problem, you'll have an object that has kinetic energy maybe and potential energy initially. And then that energy is actually going to be split between kinetic and potential, and some of it's going to go into thermal. And we talked about this when we used bar graphs, how the energy will sometimes transfer into that last bar, which is your thermal energy. So whatever you start with now can go into one of three possible places, or some combination of those. So this is going to be what we need to use here if we have thermal energy. Okay. And then it says, as with other forms of energy, thermal energy is also measured in joules. Okay, that's fine. So let's look at a problem like this, where you have a box that's sliding across a surface. These arrows on the boxes represent the box's velocity. It's traveling at 5 meters per second at A, and then 3 meters per second at B, and then it stops at C. Now, that can only happen because there must be some type of a force that's slowing the object down. And so there's a frictional force that must be pushing to the left on the box as it's moving. Okay? And so this is a problem that clearly involves friction. Whoops. Clearly involves friction. And yes, it's kinetic friction because the object is actually sliding. So let's do a thing here. And let's say that going from A to B, how much thermal energy do you transform going from A to B? So let's look at that from the perspective of saying, using the equation up at the top. We'll say the kinetic energy at A plus potential energy at A is equal to kinetic energy at B plus potential energy at B plus thermal energy. Okay, at B, I suppose. Now, there's a lot of zeros in here. Well, there are some zeros in here. And the one I would say would be the potential energy is definitely 0, because there's really no spring working here, and there's no change in height. So we don't have elastic potential energy, and we don't have gravitational potential energy. So that goes away. That goes away too. And then what you're left with is, whoops, 1/2 mass times velocity at A squared. That's equal to 1/2 times the mass, the velocity at B squared, plus thermal energy. And notice I don't have a formula to put in here. Okay. Now, these other things I know. So I have 1/2 times the mass of 1/2, because that's what I'm told up here, times the velocity of A, which is 5. I have to square it. Okay, so that tells me that my overall energy is 1/4 times 25, so 25/4 of a joule. And then over here, I would have 1/2 times 1/2 times 3 squared plus TE. So over here, I have, what is that, 9/4 joules plus E. I'm sorry, TE. So to find the thermal energy that you end up with, you would subtract 9/4 from 25/4, and that becomes 25/4 minus 9/4. That's equal to 16/4, which is equal to 4 joules. And that's how much energy you have that's been converted into thermal form. Okay, 4 joules. By the way, 25/4 that's, what is that, 6 1/4 joules. I don't need to calculate for that. 25/4 is 6 1/4 joules. So of your original 6 1/4 joules, 4 of those joules are actually going into thermal energy. And that's a lot. Let's try it from, how about if we go from A to C, how much thermal energy? I'm going to take a shortcut here, and I'm simply going to write the kinetic energy at A is equal to the thermal energy at C, because the object has stopped moving at C. And so all the kinetic energy at A is going to be thermal energy by the time it gets to C. And so in this case, my 6 1/4 joules is simply going to be my thermal energy. And that would be it. Okay. So that's how you deal with finding thermal energy. You have to find it by kind of subtracting things. There isn't a special formula for it. Let's end with one last problem here that involves potential energy and thermal energy. I'm going to read it. It says, return to our previous example. However, this time we're going to allow a package to slide down an incline from A to C, and it's going to transform 25 joules of its mechanical energy into thermal energy. How fast is it moving at C? Okay, let's try that out. So I'm going to have kinetic energy at A plus gravitational potential at A is equal to kinetic energy at C plus gravitational potential at C plus thermal energy at C. Okay, now kinetic energy at A is 0 because it's not moving, and then we have decisions to make. So we'll have to decide, why don't we make B our reference level. So we're going to measure height from B, which is probably what you guys would have picked anyway. It's just ground level. So in that case, we do have potential energy at A. It's equal to M times G times HA. That also means at C we don't have any potential. And so we're left with kinetic energy, 1/2 mvc squared, plus thermal energy. Let's plug in our data here. The mass is 1/2 kg. Gravity, let's call it 10. And the height at A is equal to 20, as in 20 meters. That's equal to 1/2 times the mass of 1/2 times the velocity at C squared. We don't know that. And we're told that 25 joules are converted into thermal, so this will be plus 25 joules. Okay, so 1/2 times 10 is 5. 5 times 20 is 100 joules, equals 1/4 velocity of C squared plus 25 joules. That 25 comes over to the other side. That gives you 75 joules equals 1/4 velocity of C squared. And multiply that times 4. So 4 times 75 joules. Take the square root. And that would be 4 times 75. 300. Square root of 300. And the square root of 300 is 17 meters per second, rounded off. And so that's what you get. That's how fast it's moving. So when the crate gets down here, it's doing 17 meters per second. Actually 17.3, whatever, it's rounded off. But notice that that 17 meters per second is less than the 20 meters per second without friction. So take a look at the example that we did a couple pages back when we solved this problem without friction. We got 20 meters per second for the speed. Now we have less, because there were some joules that were no longer available for kinetic energy. Those were these 25 joules. And so that's why we get a slower speed here. So that should make sense. When you put friction on the ramp, or if you have a ramp with friction, the object will not accelerate as much as if it did not have friction. Okay, so again, this is how we deal with friction. But using energy techniques, you just add in one more term for thermal energy, and you have to subtract that out.